Okay, so let's move on to another example here. So according to this question, you have a 15.5 gram sample of a metal which has been heated to 98.9 degrees Celsius, and then it is dropped into 25 grams of water in a calorimeter. And then it says the temperature of the water rises from 22.5 degrees Celsius to 25.7 degrees Celsius. And the question is asking for you to calculate the specific heat of the alloy. Now, there are a couple of things that come into play when you're dealing with this particular problem. First thing I want to write down here is the equation that we met before, which is Q. Okay, what's going on here? Q is equal to M times C times delta T. All right? So this is the equation that we'll be using for both the metal and the water. Another thing I want to point out here is that you're adding something that is hot, which is a metal, to something which is cooler, which is a water. And therefore, when you have that situation taking place, you're going to have the heat flow from the metal to the water. And we described this earlier when we were talking about what the definition of heat is. It's basically the energy flow resulting from a difference in temperature. And that is what we're dealing with here, right? We're dealing with something which is hotter in contact with something which is cooler, and therefore the heat flow will go from the hotter water to the cooler, the hotter metal to the cooler water. And we also said, and I want to emphasize this as well, is that this heat flow will continue until both the water and the metal are at the same temperature. Okay, so how shall we represent that? Well, first thing I'm going to write down, or the next thing I'm going to write down, is this equation, which represents the relationship between the heat that is given up by the metal and the heat that is absorbed by the water. And that relationship is simply QW, which is the heat change for the water, is equal to minus QM, which is the heat change for the metal. And of course, we have minus here because as far as the metal is concerned, it is losing heat while the water is absorbing heat. So therefore, that's why we have this negative sign. So what I'm going to do now is basically combine this equation here with what we have here. I'm going to write down expressions for QW and QM, which are similar to this right here. So the way I'm going to do that is the following. The mass of the water, which is, well, given here, 25 grams, times the specific heat of the water, times the change in temperature of the water, would be equal to minus the mass of the metal times the specific heat of the metal times the change in temperature of the metal. And then I'm going to rearrange this to get the specific heat of the metal is equal to the mass of the water times the specific heat of the water times the change in temperature of the water, all divided by the mass of the metal times the change in temperature of the metal. All right? So this is how we're going to calculate the specific heat of the metal. So it now becomes a question of plugging in the different values into this expression. So let's start off with the mass of the water, which is 25.0 grams. And then the specific heat of the water, which we already know to be 4.18 joules per gram degree Celsius, times the change in temperature of the water. And according to the question, the temperature rises from 22.5 to 25.7 degrees. So remember, it's always the final temperature minus the initial temperature. So 25.7 degrees Celsius minus 22.5 degrees Celsius. And then below that, we divide by the mass of the metal, which is given as 15.5 grams times the temperature change of the metal. Now, the initial temperature is 98.9 degrees Celsius. The final temperature will be the same as the final temperature of the water, because remember, at this point, it will be at thermal equilibrium. So I'm going to put the final temperature of water, which again is 22.5 degrees Celsius, minus 98.9 degrees Celsius. All right. So what I'm going to do is work out what's within the parentheses. So 25.7 minus 22.5. And according to my calculation, for this part here is going to be equal to 3.2 degrees Celsius. And then the 22.5 minus 98.9. And according to that, will be equal to minus 76.4 degrees Celsius. And then we work out what the specific heat is. So specific heat of the metal will be equal to 25 times 4.186 times 3.2, and then I divide that by 15.5 divided by 76.4, which is negative. Oh, and I forgot one more thing here. Very important. There should be a negative sign here. I forgot to include that here. So the result of that will be equal to .2, how many sig figs? 3 sig figs, so 0.283. And the units would be joules per gram degrees Celsius. Okay, so that's basically how that is done. All right. Okay, so we talked about calorimetry, which involves measuring heat flow in processes like reactions and so on. And I mentioned this before, and I'm emphasizing it here again. When it comes to the type of calculations that is involved in calorimetry, it comes down to this right here. Whoops. Q of the reaction is equal to the Q minus Q of the calorimeter. Because remember, when a reaction produces heat, for example, in that kind of setup, then the heat that is produced by the reaction is absorbed by the calorimeter. And the inverse is true. If the reaction is absorbing heat, it's absorbing it from the calorimeter. Okay, so as far as the calorimeter is concerned, this is the equation that we'll be using. It's the same equation as we saw before for the calculation of specific heat. Q of the calorimeter will be equal to the mass times the specific heat times the change in temperature, right? So basically, by measuring the temperature change, if you remember the setup, we have the temperature change occurring. If you remember, in that particular case, we monitor the amount of heat change by looking at the temperature change. If the temperature change is positive, that means that the calorimeter is absorbing heat, which means that the reaction is exothermic. And if the temperature change is negative, that means that the calorimeter is losing heat, which means that the reaction is endothermic. All right. So let's apply this to this particular example. So here we have a reaction between HCl and sodium hydroxide, neutralization reaction. They both have the same volume, they both have the same temperature, and they both have the same molarity. All right. So what that means basically is that the moles of hydrochloric acid will be the same as the moles of sodium hydroxide. Okay, so the question is asking, after mixing with the heat of this reaction. Now it tells you that the initial temperature is, let me see here, the initial temperature is 19.5 degrees Celsius, the final temperature is 21.21 degrees Celsius. So we need to find Q. So let me bring up the pen. So Q of the calorimeter will be equal to the mass of the solution times C of the solution times the change in temperature. All right. Now, in this particular case, we can make some approximations, which actually are very good approximations. For one, we're going to assume that the density of the solution is the same as the density of water, which is 1.00 grams per mil. All right. Another thing we're going to assume is that the specific heat of the solution is the same as the specific heat of water, which is 4.18 joules per gram degree Celsius. All right. So those are two assumptions we can make in order to solve this problem. So in this particular case, the mass, let me do this over here. Well, where should I put this? Let me put it here. The mass of the solution would be equal to the density multiplied by the volume. The density is 1.00 grams per mil. And the volume would be 50 mils plus 50 mils, which would be 100.0 mils. So that is going to be equal to 100 grams. All right. So in this equation, the Q of the calorimeter, we're going to place here. Mass, 100 grams, times the specific heat, which is 4.184 or 4.18 joules per gram degree Celsius, times the change in temperature, which is the final temperature minus the initial, which would be 21.21 degrees Celsius minus 19.5 degrees Celsius. So let me do that calculation and see. So 21.21 minus 19.5. So that's 1.71 times 4.18 times 100. So according to my calculations, when rounded off to 3 sig figs, Q of the calorimeter is equal to 107 joules. All right. Now, that represents the Q of the calorimeter, which means that Q of the reaction is equal to minus 107 joules. Okay, and I think that would be the solution to this particular problem. Now, let me just take this a step further, because you could be asked for the enthalpy of the reaction, in which case you have to write down what the equation is. And the equation for this reaction is the acid-base reaction between sodium hydroxide and hydrochloric acid to form sodium chloride and H2O. All right. Now, in this case here, it's a one-to-one mole relationship. So what we need to do is find the moles of each reactant. So the moles would be equal to, based on the information provided, the concentration, which is 0.250 moles per liter, times the volume in liter, which is 0.050 liters. So when we do that, we're going to get, according to my calculation, when rounded off to, actually this should be 3 sig figs. So let me do this. So this should be an extra 0 here, and the answer here will be 0.0125 moles. So therefore, delta H for the reaction, which is the enthalpy change, is equal to the enthalpy, the Q reaction, which is minus 107 joules, divided by 0.0125 moles. So 107 divided by 0.0125. So according to my calculation, this works out to be equal to, let me squeeze this in down here, 8560 joules per mole. And that's how that is done. All right. Okay, so that's yet another example utilizing the calorimetry calculations or equations that we just learned. Okay, Now, oh, actually, we just did this problem here, right? So the very last step that I did down here, I didn't realize it. Let me just indicate what I'm talking about here. The very last thing that I did down here, circulating all of this here, is actually the answer to the question that is asked on the next slide, right? Okay, so we don't need to do that because we did it already. All right. I'm going to stop here again for this video, and I'll continue with a discussion of bomb calorimetry in the next video.